So hi everyone, welcome on this channel. I'm Nikki, and in today's video we are going to see how to perform a DME arc. All right. So there are two types of DME arc. The first type is when you are actually coming from the station, enter the DME arc, and then you exit. All right. And the second type is when you are actually coming inbound the station, you do a turn, enter the DME arc, and after some point you decide to exit the DME arc, right? The exit is basically the same as the entry, all right? It can either be outbound like this, or it can also be inbound, all right? And we will cover both cases in this video. But first, we are going to cover the case where we are actually coming from the station, all right? So I'm going to draw a proper VOR DME here, all right? Like this, tack, with a small rectangle to symbolize the distance measuring equipment. And from this DME or this VOR, I will come follow radial outbound, all right? And at some point I will, I did a mistake. Right, so we come follow radial outbound, and at some point we will do a 90 degrees turn like this, and we will enter the DME arc. At some point we will do the exit, all right? So the DME arc is made of three steps. The first one is the entry right here. The second one is the tracking, which is basically all this part here. And at some point right here, you will do a turn anticipation in order to exit the DME, right? So I will erase all of that. So let's say that you want to do 10 DME arc, right? So you will actually need to start turning before reaching 10 DME, because if you wait to reach 10 DME, for example, 10 DME is here, all right? So if you continue to and reach 10 DME and you start turning there, you will actually overshoot the arc, and you will need to do like a nasty correction in order to come back on the desired track, all right? So you need to turn before, but the question is, when do you need to turn in order to do this 90 degrees turn? So let's assume for a second that we do not want to do 90 degrees turn. We want just to do a simple circle like this. All right. All right. So the circle is not perfect, but you get the idea more or less. All right. So like this. As you can see, the distance at which we have to turn. All right. So here is 10 DME. All right. The distance at which we need to turn is actually equal to the radius of our airplane's turn, of our of our airplane's turn. All right. And what we need to do before entering a DME arc is actually calculate our radius of turn. All right, like this. All right, so we are going to step aside, and we are actually going to determine what is our radius of turn. When we turn, in civilization, we are actually turning at rate 1 turn, which is rate 1 turn, which is equal to 3 degrees per second. All right, we will keep this in mind, and we will come back to it. So, all right. So now I'm going to draw a circle here. All right. And this is just like a circle that an airplane would fly if you were like constantly keeping the bank angle of a rate 1 turn. Right, it will keep turning into a circle. And the distance that you are going to travel on the circle will be equal to 2 times pi times the radius of turn. All right, now I will draw another circle. I will do something like this. All right. And as you see, I am not flying an entire circle. I am only flying, let's say right now it looks like a quarter, but we don't know. It's actually, we are actually flying a certain amount of degrees on the circle. All right, so this is when we are actually flying 360 degrees, and this is a case where we are actually flying an unknown amount of degrees on the circle. And in that case, we could get a formula which looks like this. The distance will be equal to 2 times pi times the radius times the angle that we are actually traveling over on the circle divided by 360. All right. Where that comes from? Well, actually, it comes from a cross product. So, for example, for 300, I will draw it. I will erase that and write it properly. If for 360 degrees we have the distance which is equal to 2 times pi times the radius, what would it be equal for an angle of 8 degrees? All right, and we do a small cross product. All right, so what's in the diagonal is actually on top of the fraction, so it will be 2 times pi times the radius times the angle, and what's actually on the other side goes below, so it will be divided by 360 degrees. This is the reason why we have this formula right over here. All right, so I will just write it properly just here. So the distance will be equal to 2 times pi times the radius times the angle, and all of that divided by 360. All right, and just to confirm it again, that's if you want to fly over a circle, but just a certain amount of the circle. You don't want to fly the entire circle. You don't want to fly 360 degrees. You would just want to fly over this part, which is just just here, right? Like this. All right. If we actually divide each side by the time, all right, it will be equal to distance divided by the time, which would be equal to 2 times pi times the radius times the angle divided by the time, and of course divided by 360. All right, so the distance divided by the time would be equal to the airplane speed. All right, in our case, what's interesting us is the ground speed of the aircraft. All right, so I will write it just here in blue. So that's the ground speed. All right, and the angle divided by the time is actually something we call the angular speed, which we'll write whiskey like this. All right, that's the angular speed. I will write it here. Angular speed, and it will be in degrees per a unit of time, right? So it could be minutes, seconds, or hour, right? Divided by the time, and that's what we have actually, an angle divided by the time. So right now we will just focus on the fact that the angle of the time will replaced by the letter whiskey. All right, and that actually represents the time at which we are going to cover the circle right over here. Right. So if we want the radius, right, which is right here, we are going to actually displace some parts of the formula. So we will find ourselves with, first of all, I will rephrase the formula. So it will be equal to the speed divided by t well, the speed which is equal to 2 times pi times the radius times the angular speed, and all of that once again divided by 360 degrees. Right? Now we want the radius, as I said, and we are going to need to reform the formula. So the radius would actually be equal to the speed of the aircraft ground speed divided by 2 and pi, and also by the angular speed multiplied by 360. All right, so we got our formula to get the radius. The only thing is that we actually do not have the angular speed. All right, but what we know is that the airplane is, as we said before, is here it is actually turning at a rate 1 turn, which is equal to 3 degrees per second. All right, and I will move aside for 1 minute probably, like this. And for example, if on a circle, all right, this is a circle, this represents a circle when we are actually turning at a rate 1 turn, all right? We are on the top of the circle, all right, and we are actually turning clockwise, all right, so we will be like this. Our relative position to the center of our turn will be 360, all right? We are of the center of our turn. If we do a 90 degrees turn, all right, our heading will also move by 90 degrees, all right? Our heading is 90 degrees. Here it was 090, and here it's not 090, it's 180, and our position 090, all right? So we see that there is a relation between the heading change of our airplane and our relative position to the center of the circle over which we are flying, all right? And the relation is that they are exactly the same. So when you have an airplane which is actually turning at a rate of 3 degrees per second on a circle, it means that the relative position to the center is also moving by 3 degrees per second, all right? And this actually gets us the angular speed of the aircraft, all right? Note also that the radius is in nautical miles. The ground speed is in knots, all right, which actually is nautical miles per hours, all right. So if we want to have the formula, which is we want the formula to be completely correct, we actually need the angular speed to be in a certain unit. In our case, it will be degrees per hour, all right? It's very important to have it in hours, all right? And the angular speed is, as we say, 3 degrees per second, which is equal to 180 degrees per minute, and which is equal, well, I will not calculate it, but it will be equal to 60 times 180 degrees per hour, all right? So at the end of the day, we will find with something like this. The radius is equal to the ground speed of the aircraft times 2 times pi times what we have just here. So 60 times 180, 60 times 180, and all of that multiplied by 360. All right. If I write the formula in another way, it will be something like this. It will be the ground speed of the aircraft times 2 times pi times 60 times 180. All of that divided by 360. I will just do some brackets here. All right. All right, and what we just got here, 2 pi times 60 times 180 divided by 360 here, is actually equal, you can actually do it at home on your calculator, is actually equal to 188. All right, so at the end of the day, the radius of turn will be equal to our ground speed divided by 188, which is actually quite difficult to calculate when you are in an aircraft. It's actually difficult for me to calculate it with my mind right now. So in order to make it easier to calculate, we will actually round up 188 by 200. All right, and that's probably one of the formula that you have seen in your IFR training manual. All right, the ground speed divided by 200, which is, and this formula is actually valid when you are turning at rate 1 turn. All right, so that's really important. All right, so we actually got the radius, which is equal to our ground speed divided by 200. But here's the thing. I will just draw it in purple. So at this very point right here, which is the anticipation point, we will calculate a distance at which we should be at range 1 turn. All right, and so at this position right here, the airplane should actually be banking. All right, it should already be at range 1 turn. So we should start turning slightly before right here. All right, right here we will be straight and level. All right, we should actually allow some time for the airplane to actually take the bank angle required to do a rate 1 turn. All right, and at the speed at which we are actually flying, it will take a bit of distance to actually reach the angle of bank required. All right, and we actually need to prepare for that. So when we are calculating for the distance before which we should turn, right, we should add a small additional distance in order to compensate for the time that it takes to pass from a straight and level position to position where we are actually at the bank for rate 1 turn, right? So I will explain it later this right now, but for example, if you are flying at, let's say, 120 knots, all right, that's in the ground speed, all right, and you want to do a 10 DME arc, all right, according to the formula that I have just showed you, you would need to actually turn at 120 divided by 200, which would, so I remove 1 0 on each side, 12 divided by 20, which is basically equal to 0.6. All right, so I would need to actually turn before reaching 10 DME. So 10 minus 0.6 means that I would need to turn at 9.4 DME. All right, but that's without taking into consideration the fact that we actually need some time to turn at a rate 1 turn. So when you are actually flying at speeds which are between 80 knots up to 140, all right, I recommend adding 0.1 nautical miles to the calculation that we have just made. All right, so that would give us 9.3. That's the distance at which we should actually play with the stick in order to start our bank and reach rate 1 turn. All right, from 140 up to 200 knots, I recommend to add 0.2 nautical miles. All right, and from 200 up to 250 knots, I recommend adding 0.3 nautical miles. All right, let's do a couple of exercise. All right, so let's say that we are actually flying at 100 knots. All right, and I want to do 8 DME arc, and we are actually coming outbound. So basically, this is the situation in which we are. We are actually moving outbound, and we want to do 8 DME arc, right? At which distance from the viewer station are we supposed to start moving the stick in order to turn and arrive at 90 degrees at 8 nautical miles? All right. So for that, we have to apply the formula that we have seen before. So 100 divided by 200, which is equal to 0.5. That's the radius of turn. All right. And we are actually flying between 80 and 140 knots. All right. So we need to actually add 0.1, which is equal to 0.6. All right. So we need to actually turn 0.6 miles before reaching 8 DME. All right, and that would give us 7.4 nautical miles. All right, so when we are actually at 7.4 DME, we start turning, and by turning at 90 degrees, when we reach the 90 degrees, we will actually be at 8 nautical miles, and we will be on the DME arc. All right. Let's try another one. So let's say that you are actually flying at, let's say, 160 knots. All right. You want to perform a 12 DME arc, and you are actually coming inbound. All right. So I will draw it. So you have the viewer station here, and you are coming from the top. You are coming inbound, and at some point you need to turn and perform the DME. All right. At which, so that's 12 DME, and at which distance from the viewer station are you supposed to actually turn? All right. So if we apply once again the formula that we have seen before, we are going to determine the radius of turn, which is 160 divided by 200, all right, which will be equal to 0.8. All right. Moreover, as we are flying between 140 and 200, we will need to add 0.2 nautical miles, all right, in order to anticipate for the time that it takes to reach the back angle required. All right, so plus 0.2 like this, and that would be equal to 1. All right, so we actually need to turn 1 nautical mile before reaching 12 DME. All right, and that would give us 13 DME. All right, so at 13 DME, we are supposed to turn, actually, we need to turn left. And when we will reach 90 degrees to our left side, we will actually be on the DME arc at 12 nautical miles. All right. Yeah. So here's the thing. When we are turning, we are actually turning at a range one turn, as I said many times before. But here's the thing. There are like two ways of determining the bank angle required to reach range one turn, right? The first technique is to take the speed at which you are flying, the true air speed, right? I will just do it here. True air speed. You divide it by actually 10. Yeah. All right. And you will add half of what you have just calculated. All right. Right, so I'm just going to give an example. So for example, if you are flying at 120 knots, it means that you are, in order to reach a rate 1 turn, you will need to have a bank angle of 120 divided by 10, which is equal to 12, and you will add half of 12. That will be equal to 6. All right, it will give you 18 degrees bank angle. All right. The second technique is, I think, a bit more famous, which consists in taking the true airspeed divided by 10 and then add 7. All right, it will give us like 120, so 12, and we will need to actually add 7, which will be equal to 90 degrees. Right. Note that mathematically, the first one is slightly more precise. All right, but they are more or less the same. What I want to show you is that when you will actually reach, let's say, 200 knots, all right, with the first technique, all right, you will have to take then 20 plus 10, which will be equal to 30 degrees. And if you use the second one, it will be 20 plus 7, which will be equal to 27. All right. So in both cases, you will reach 30 degrees, and it's usually when you want to do a turn, you don't go at more than 30 degrees. All right. If you go more than 30 degrees, it means that it is probably a skill test where you are required to turn at 45 degrees or 60 degrees bank, but that's not something you will actually do when you will be in an airline. All right. Usually, when you are flying for an airline, you are limited to 30 degrees. All right. So what happens when you are actually flying between 200 and 250 knots? All right. Well, the formula in that case would be to use that. All right. So you take your ground speed, you divide it by 100, and then you subtract 1 out of it. All right. So for example, if you are actually flying at, let's say, 220 knots, and you want to do, let's say, a 6 DME arc, all right, you need to calculate the radius of turn, which will be equal to 220 divided by 100, which is equal to 2.2. Yeah, and you will need to subtract 1, which will be at the end of the day equal to 1.1. All right, and to that you will need to add what I just told you before. You are between 200 and you're actually between 160 and 250, and you will need to actually, no, I'm mistaken. You are actually between 200 and 250, and you will need to add 0.3 nautical miles. So it will be equal to 1.4 nautical miles at the end of the day. All right. And the thing about this formula is that it is only valid when you are actually flying between around 200 knots. So it's only valid between 180 knots up to 250. And moreover, this formula does not take into account the fact that we are turning at a rate 1 turn. It is taking into account the fact that we are actually turning at a bank angle of 30 degrees. All right, and that's what's very interesting about this formula is that it allows you, with the other formula that we have seen, it allows you to actually enter a DME arc accurately, whichever is your type of airspeed and your type of aircraft. All right. So we're now on Explain 11 with a Cessna 172 Skyhawk equipped with a Garmin 1000. On the left-hand side of the screen, you can actually see that we have a Jepson chart, which is an SID of Sevilla Airport. And as you can see, we have a DME arc, and we are going to do the entry of this DME arc. Right now, we are at straight line level at 3,000 feet. We are on radial 275 of Sevilla Airport. All right, so we are on this radial right over here. All right, and we are at 14 nautical miles out of the station, so we are very near to the turn. All right. We have to calculate the radius of turn, and for that we have the true airspeed right over here, and we have the wind. All right, we have no wind at all, so in these conditions the ground speed is equal to our true airspeed, which is 120 knots. All right, so I will just draw the situation right over here. So we have the station. We are actually going outbound. At some point we are going to turn and perform the DME arc. All right, so we are going to turn somewhere over here. Our ground speed, I will not write it in blue. Our ground speed is 120 knots, and we have to perform a 15 DME arc. All right. So if we use the calculations that or the formulas that we have seen before, our radius of turn will be equal to the ground speed, 120 knots, divided by 200, which will be equal to 0.6. All right, and as our ground speed is between 80 and 140 knots, we actually need to add 0.1. Right, and all of that will be equal to 0.7. All right, so we actually need to start turning 0.7 miles before reaching 15 DME. So at the end of the day, we actually need to start turning when reaching 14.3 nautical miles from the station. All right, and we are actually at 14 nautical miles, so we have 0.3 miles to go. So I will now unpause the simulator, and when we will reach 14.3 DME, we will actually do a 90 degrees turn to the left. I can already set the heading bug to help us. All right, like this. All right, and I will unpause the simulator. Like this. All right. So we are now at 14.1 DME, 0.2, and we are now at 14.3, and we turn at the rate 1 turn, which is indicated right over here. When the magenta line is actually touching the small line right in front of my mouse, it means that we are turning at the rate 1 turn. Right, we are now at 14.9 miles, and we are supposed to get 15 nautical miles right now. All right. All right, and I can roll out like this. So as you can see, our formula works very well when the airplane is at low speed, at least. All right. All right, now we are still on Explain 11. However, we have changed the plane. The plane is now an A320. We are still at 3,000 feet. We are still on radial 275 of Sevilla VOR, but our speed is changed and is now at 240 knots. All right. Moreover, the auto thrust is maintaining the speed for us. All right. We have almost a wind which is equal to 0. All right. We have 1 knot of crosswind coming from the right, so it will not impact our entry, and our true airspeed and ground speed are basically the same. They are at 250 knots. All right. We need to do 15 DME arc, and we won't be able to enter the DME arc at a rate of 3 degrees per second without exceeding a bank of 30 degrees. All right, so how are we going to do? We are going to enter while maintaining 30 degrees. All right, but we will need to apply the second formula that we have seen before. So we take the ground speed, 250, we divide it by 100, which gives us 2.5, and then we subtract 1. All right, and we find ourselves with a radius of turn of 1.5 nautical miles. All right. Moreover, we need to apply 0.3 nautical miles in order to compensate the distance that we will fly when passing from the state where the aircraft is straight and level to a state where the aircraft is actually banking at 30 degrees. All right. So yeah, in total, we will need to turn 1.8 nautical miles before reaching 15 DME. All right. So at 13.2 nautical miles from the station, we will start doing our turn. All right. So we have about 4 miles to go before turning right now, and we are going to do roughly a 90 degrees turn to the left. Right. Why do I say roughly? Well, this is because when you enter an arc, and when you are on a DME arc, actually, you always want the track of the aircraft to be perpendicular on the radial on which we are. All right, but as the radius of turn, as the radius of turn of the aircraft will be quite large. All right, it is quite likely that the radial on which we will be and the radial on which we are actually won't be the same when we will be at the end of the turn. At the end of the entry into the DME arc. All right, so 1 mile to go. I will disconnect the flight directors and the autopilot. All right, so 30, and now we can turn. Here we go. All right, and I will just change the heading bug. Like this on heading 180. I will correct for the altitude. All right. And 14.9. And now I can start to roll out. And we are just on radial 265 at 15 miles from the station. All right, so we have managed to do a good entry. All right, so now we know how to perform an entry, but we actually need to learn how to actually track a DME arc. All right, there are 2 ways to do that. The first way is called turn 10, twist 10. Right, it is the most basic way to track a DME arc, and it is the first one that we will actually learn. All right, so let's say that we have our station right over here. We are going to draw some radials like this, and another one here, and we are going to draw the DME arc. All right. Here, let's say we have radial 090, here radial 100, radial 110, 120 here, and 130 over here. All right. So what we're going to do is that instead of flying a curved line like this, all right, which would require the airplane to be constantly banked, we will actually fly from intersections to intersections. That's not very well done. I will try here. Yeah, like this. All right. Then I will draw another one here, like here, like this, and like this. All right. So we are going to fly constant heading from point to point. All right, and we are going to change our heading every time we pass a point. All right. Moreover, I would like to point the fact that this is the radial 100. All right. I will draw it again like this, and we do not want to fly perpendicular to it. All right, if we were to fly perpendicular to it, we would actually overshoot the DME arc. All right. Moreover, if we were to fly at an angle of 100 degrees, we would fly something like this, which would make us undershoot a lot the DME arc. So what we want to do is to always have a constant angle between the radial that we have crossed and the heading that we are flying of, I will draw it again like this, of 95 degrees. All right, 95 degrees. All right, so let's say that we are on radial 100. We would actually want to fly on heading 195. All right. Once we cross radial 110, we would actually want to fly on a heading of 205. All right. So we are actually twisting our heading by 10 degrees. That's what we would be flying if we would continue on heading 195 after crossing radial 110, and we would actually overshoot. So what we want to do is to actually turn our heading knob by 10 degrees. All right, and at the same time, we want to prepare to cross the next radial, and for that we would need to actually twist our OBS, omni-bearing selector, by 10 degrees, and we are going to do that again and again until we reach the end of our DME arc. All right, so right now we are heading 205, and we want, once we reach radial 120, we want to actually turn our heading bug by 10 degrees. So it will be on heading 215, and we want at the same time to change our OBS, to twist our OBS by 10 degrees, and this is why the technique is called turn 10, twist 10. All right. Moreover, we need to, but in order to keep tracking the DME arc, we need to keep track of the distance. All right. So let's say we want to do, this is a 15 DME arc. All right. Every time we cross a radial, we want to be at 15 DME. All right. At each intersection, we want to be at 15 DME. And as you see, our segments are all actually undershooting the arc, but that's something that we are voluntarily doing. So once we pass an intersection, our DME indication will decrease down to, let's say, 14.9. All right, and once we cross the middle of the segment, let's say it will indicate 14.8, the DME indication will actually increase again, so 14.9 again. And once we reach the radial, if we are on track and we have done no mistake and the wind is not drifting, making us drift, it would indicate 15 nautical miles again. And this is how we are actually flying a DME arc, by actually dividing the arc in multiple sectors. All right. There is another thing we need to see. If, for example, we have a viewer here, and I would draw the different radials over here, right? And the DME doing that. Actually, I will draw it again. All right, and I will draw the intersections right here with a segment here. I will draw it again like this. All right, here's radial 090, here's radial 100, and here's radial 110. All right, so on this segment we are supposed to fly on heading 185 because we have 95 degrees to add to our radial. All right, here when we will arrive at this intersection, we will have to fly on heading 195, and after passing radial 110, we'll need to fly on heading 205. Alright? But here's the thing. If for some reason when you cross the radial 100, you are not passing 15 DME, you are actually passing 14.7. It means that you are actually undershooting. That would be your track. Alright, so if after passing this radial you start taking heading 195, you will actually continue undershooting, and so for the rest of the DME arc. So what you want to do is to first continue on your heading, alright, and then you will start taking the heading that you have calculated before, so 195. Alright? If we do the same thing, if we are overshooting, alright, I will draw it again, here, with the arc like this, the path, alright? If we are overshooting here, right, this is our path, right? If we take directly the heading that we had calculated before, we would continue to, I want the orange, not the red. We would continue to overshoot for the rest of the DME arc, alright? So first, instead of directly taking the heading that you had calculated, which was, I think, 1905 here, alright, 1905, you want to take the heading and add 10 degrees to it, alright, and once you hit 15 DME or 14.9, then you take the heading that you had calculated, alright, like this. Alright, so when you are undershooting, you continue on your actual heading, and once you hit 14.9, 14.9 or 15 DME, you take the heading that you have calculated. Alright, but if you are actually overshooting, you turn not by 10, but you actually turn by 20, and once you reach the distance 14.9 or 15, you actually take the heading that you have calculated. Alright, so you actually remove 10. Alright, so we are back on X-Plane 11 with the same example as we had before. We are still at around Sevilla airport, and we are going to perform a 15 DME arc. We will need to turn on the left. We are actually having a true airspeed of 120 knots and no wind, so our ground speed is 120 knots. So our distance of anticipation will be 0.7 nautical miles before reaching 15 DME. So we will start turning when reaching 14.3 nautical miles from the station. Alright? Right now we are with the autopilot on, and we will need to do a 95 degrees turn. Alright, so we will take 275 minus 95 degrees, which will give us 180. Alright, so our first heading, once we enter the DME arc, will be heading 180. Alright, I will unpause the simulator and we will continue. And we are now at 14.3 nautical miles from the station, and we start our return, and the autopilot is now following the heading. We are turning at rate 1. You can see the magenta line on the small line right over here, and we can already set our next radial, which will be heading 265. Alright, and we are on our heading at the right distance, 15 DME. Alright, so now we are crossing radial 265 and we are at 15 DME, so we are on track and we can actually start turning by 10 degrees and then we'll twist by 10 degrees. As you can see, we have reached 15.1, so we are actually overshooting. So what we need to do is to add 10 degrees inside the turn. Alright, and now we are reaching 15 nautical miles, so we are back on track and we can come back to our initial heading of 170. Alright, and we turn back like this, and this is how we correct for the distance differences that we can actually find when passing through an intersection. Alright, so now we are passing radial 255 and we can start turning by 10 degrees. So set a heading of 160 and prepare our next radial. We will twist it by 10 degrees, so it will be radial 245. Alright. Now, for the purpose of the exercise, I will voluntarily overshoot the DME arc. Alright, I will change our actual heading by 5 degrees and it should actually make us overshoot when we pass through the next intersection. Alright, I will take our initial heading back, which was heading 160. Alright, so now we are passing through the radial and we see that we are overshooting. So what we need to do is to first set our next heading, which will be heading 150. Alright, and then I will need to actually add 10 degrees in order to recover the path, right? Because right now we are flying parallel to the path with a distance of 15.2. So if we continue like this and we apply the technique without applying any correction, we will continue doing a DME arc, but it will show 15.2 on the DME indication. All right, and I can set the next radial, which will be radial 235. Like this, and you see that we are slowly recovering the distance. Alright, and we passed 15 DME and we can take our initial heading back again, and it was heading 150, which is radial 235 minus 95 degrees. And now that we crossed the radial, we see that we are at 15 DME, so we are back on track, and we can now turn 10 and twist 10. Now, for the purpose of the exercise, as before, we'll simulate an undershooting. All right, so I will voluntarily change our heading in order to make us undershoot the DME arc. Alright, I will take back my initial heading of 140. Alright, and now we come across the radial and we see that we are actually undershooting. So what we need to do is to set our initial, our next heading, which is heading 130. Alright, and then we actually add 10 degrees, so we come back on the heading on which we were before. Alright, so heading 140. And we can twist our OBS, and the next radial will be radial 215. Right? And we are actually slowly recovering the distance. 14.9, and we should hit 15 DME soon. Alright, and now we can recover our initial heading, which was heading 130. And now we are passing through radial 215, and we can start turning by 10 degrees and twist our OBS by 10 degrees too. Alright, so the next radial will be radial 205. So we are now on radial 135, and if we have a look at the map, we can actually see that we have a very round path. All right, it is not as curved as what we could find on the Jepsen chart. However, the turn 10 twist 10 technique is one of the most basic way to accurately keep track of the DME arc. The turn 10 twist 10 technique, which is the first one that we have learned, uses an OBS, which is an omni-bearing selector, and a CDI, which is a course deviation indicator. The second technique that we are going to learn only uses an RMI, which is a radiomagnetic indicator. And the goal will be to always keep our track perpendicular to the radial on which we are. So for example, if I draw, that's a VOR station, right, with a DME, I draw a DME arc right over here. Well, it's not perfect, so I will draw it again. Alright, well, it's slightly better, but it's not perfect. And like this. Yeah, way better. Alright, we will want to keep our track perpendicular to the radial on which we are. So let's say that we are right over here. Alright, I will draw an RMI like this. Alright, our heading is in green, right over here, and we want to keep the head of our needle perpendicular to our heading. Alright, that way we know that we are perpendicular to the radial on which we are. Alright, see if I draw a line like this. Alright, you see that the heading and the needle are perpendicular. So it means that we are actually tracking the DME arc. Alright, and I forgot to precise that this is in no wind condition. Alright, where the track is actually equal to the heading. All right, I will draw it again here. So that's our airplane, that's our truck, all right, and that's our radial, all right. And as you see, the needle is always pointing towards the station and is always perpendicular to our track, all right, which in our case is always perpendicular to our heading. All right, now let's say for a second that we are having this on our RMI. All right, that's our heading. All right, and instead of having the head of the needle 90 degrees to our heading, we will have it slightly above the reference, right? That illustrates the situation in which we would be actually flying away from the arc, and we would be closing to the station, all right? It would be that situation right over here. So that's our plane, that's us flying away from the arc and getting closer to the station, all right? And we would have the needle right over here, all right, and not at not 90 degrees on the left of our track, all right. That illustrates this situation right over here. In the other case, if we are actually trying to fly away from the arc, but we are also trying to fly away from the station, which is that case right over here, we would actually fly something like this. All right, that's the RMI, that's our heading, and that's the 90 degrees reference. All right, and the needle would actually be located, the head of the needle will actually be located below the reference. All right, it will be something like this. All right, and here's the 90 degrees to the track, all right, and you see that the needle is actually below, all right. So as a general rule, I will draw it again right over here. All right, that's our heading, and that's the reference where the needle has to be if we want to fly an arc around a station. All right, if for some reason the needle is not located at 90 degrees, if it's located, let's say, slightly above, right, from here up to there, all right, it means that we will actually get closer to the station, all right, so the distance will decrease. On the other hand, if the head of the needle is actually pointing below the reference, all right over here, we will actually get away from the station, so the distance will increase. And this is how we actually correct for the distance if we for some way we are actually not on track and at the right distance. All right, let's say for example I have an RMI, all right, that's the needle, that's the heading, and the DME indicator shows that instead of flying at 10 nautical miles from the station, I am actually at 9.8. All right, so in order to correct for that, I will need to fly towards my arc, and I will need to change the heading and turn slightly on the right in order to put the head of the needle, sorry, I will set it again. Instead of, I will have to put the head of the needle slightly below the reference in such a way that I will increase the distance from the station and recover the 10 DME arc. All right? And what I've just explained so far works for the no wind condition, all right? When we have some wind, we will have to actually set the reference somewhere else. So for example, let's say I will draw an arc like this. And this is the center of the arc. Let's say this time that the wind is coming from the east, all right? So our track is going to be like this, all right? Always perpendicular to, I will draw it in blue, always perpendicular to the radial in which we are, all right? That's a perpendicular sign. It's not very well drawn, but it will make it. But our heading, in order to keep this track, will have to be moved slightly on the side. So when we are in our cockpit, the RMI will look like this. So this is our heading, all right? Our track will be slightly on the left, right over here, but some aircraft shows it, but sometimes some aircraft don't display it, all right? So we will remove it. And instead of having the reference at 90 degrees, the reference will be slightly below, all right? And the needle will be like this, all right? Well, actually, I will draw the track. And this is because we have a wind correction angle, all right? Actually, the wind correction angle is the other way around, but the drift will actually make us move from this heading to this track here, all right? And if we have, let's say, a wind coming from the left, we will have the other, it will be the other way around. The track will not be here anymore, it will be right over there, all right? And we will have the reference set over here, all right? Oh, I will do it in blue. Oh, like this, in blue. All right, and once you have set the reference on which you need to keep the head of the needle, the technique to actually get closer or get away from the station works too. So for example, let's say we have a wind coming from the left, all right? We can disregard this arrow right over here. We are actually in this situation where the reference has to be slightly above the reference in no wind condition, all right? If you are putting the head of the needle slightly above the reference, you will get closer to the station, all right? And if you set the head of the needle below this line, below the reference line, you will actually get away from the station, all right? And this will be how you will correct your distance while being on a DME arc. Moreover, I would like to point out the fact that right now, let's say we are going to forget about this, and the wind is coming from the right, all right? When you will be at the top of the DME arc, the wind will not be coming from the right, it will be tailwind now, all right? It will be pushing you. And when you will be on the other side of the arc, right over here, the wind will be coming from your left, all right? So the wind is not always constant, and you always need to calculate in your brain, with your brain, you always need to calculate the wind correction angle and ask yourself where the wind is coming from and where you have to correct. And that way you will actually always be able to set the reference on which you have to set the needle. All right. So when you are tracking a DME arc, you always want to ask yourself where the wind is coming from. All right, the wind direction. All right. You then want to calculate the wind correction angle. All right. I will do a video about that soon. Then you need to set the reference which is the point where you need to put the head of your needle in order to follow a curved line, which is the curve of the DME arc. And the last thing you need to do is to decide whether you set the head of the needle above the reference, at the reference, or below. In the case where you want to get closer to the station, if you think that you are on track and that you only need to basically turn around the station. And the last case is when you actually are closer to the station and you want to get away from it in order to recover the correct DME distance. All right, you want to decide if you go on the reference point or not. All right. Alright, so we are back on Explain 11, and right now we are performing a 10 DME arc around Sierra Oscar Romeo VOR. As you may see, the box right over here has a small distance indicated in it, alright, and this is the DME distance. Right below it you have another box which also indicates another distance, but this distance is actually a GPS one. Alright, and right now we are using a Garmin 1000 and we are displaying a bearing, which is the needle in blue right over here. Alright, in order to display the bearing, you actually need to press P of D and then press bearing 1. Alright, and you get the bearing to the station that you have selected in nav1. Alright, and as you see right now, we don't have any wind at all, so we need to keep the head of the needle on the reference, which is represented by the small line right over here on the mouse, and this little mark is actually located 90 degrees away from our actual heading. Alright, let's say for a second that we want to get closer to the station, we need to put the head of the needle above this reference. Alright, so we will turn slightly on the right like this. I will put, let's say, 10 or 20 degrees above it. As you see, the GPS distance is decreasing, and now the DME distance is decreasing too. Alright, we are at 9.9 and now we are at 9.8, and if we want to get away from the station, and if we want to increase the distance between the station and us, we want to set the head of the needle below the reference that we have set. Alright, so now I will turn left. The head of the needle is passing below the reference, and we see that the distance has stopped decreasing, and it will now increase again. We are now at 9.8, 9.9, and now we are at 10 DME, so we need to set the head of the needle back on the reference, and we will continue our DME arc. And now we are at 10.9, so we need to actually set the head of the needle slightly above the reference, like this. And 10.0, and we set the head of the needle back on the reference right over here. Alright, and then we continue to do the DME arc, and we continue to keep the head of the needle on the reference that we have set. We are back on 10.1, so we need to set the head above in order to get closer to the station. Alright, like this. I will correct the altitude. During your RA4 skill test, you will be allowed a 100 feet difference between the altitude that you have set and the altitude at which you actually are. Alright, and as you can see on the map, we are actually doing a very nice and very curved DME arc. All right, there is no, you can see there is no sectors or straight line. You are always doing a slight bank on the sides, on the right side, and the line is actually as curved as what you have on the chart. So now we are still doing a 10 DME arc. However, as you may see right over here, we have 15 knots of crosswind. All right, and if we keep the head of our needle 90 degrees to our heading, we will actually get pushed by the wind and get closer to the station, and we will undershoot the arc. Right now the GPS distance has changed to 9.9, and now it is changing, the DME distance is changing to 9.9 also. Right, so we are getting closer to the station. And in order to correct for that, as the wind is coming from the outside of the arc, we need to set the head of our needle slightly below the 90 degrees mark. But by how much? In order to determine by how much you need to set the head of the needle below the 90 degrees mark, you actually need to calculate your wind correction angle. All right, we are actually at 126 knots, all right, of true airspeed, and we have 18 knots of crosswind. So we need to basically apply 9 degrees of wind correction angle. All right, so we actually need to set the head of our needle 9 degrees below the 90 degrees mark. All right, and we do that by turning to the left. And like this, all right? The head of our needle is now basically 9 degrees below the 90 degrees mark. Right now it's 10 and now it's 9, like this. All right, and by keeping the head at this position, all right, we will keep tracking the DME arc at 9.8 nautical miles, but what we want is 10. All right, so remember what we've seen before. If you set the head actually above the reference, which is right over here, we will actually be closer to the station. If you set the head below the reference that we have set, which is an imaginary line which is located right over here, we will get away from the station. All right, so we need to set the head below the reference, which we are doing right now. All right, and you see that we are actually getting away from the station, and we are now at 9.9. We were at 9.8 before. And now we are at 10 DME, and we can turn right in order to get the head of our needle back on our imaginary line, which is the reference and which is right over here on the mouse. All right, and by doing so, we managed to actually keep track of the arc while having some wind. Alright, and as you can see, by doing so, by using this technique, by setting the RMI and the needle head on a reference, which keeps your track 90 degrees to every radial, you actually manage to do a very curved line. So we have seen how to perform an entry, we have seen how to track a DME arc, and now we are going to learn how to do a proper exit from a DME arc. So I will draw a DME arc right over here, right? I will put the station right there. That's one radial. Here's another, and we have seen at the beginning of this video that the radius of turn, we will write it r, the distance that we travel on the arc, right over here, the distance d, and the angle that we are covering while moving on the arc are actually linked by a formula, and this formula is equal to the distance is equal to 2 times pi times the radius times the angle divided by 360. Alright? Pi is equal to 3.14 and multiple numbers comes after that, which roughly equals to 3. Alright, so 2 times pi is basically equal to 2 times 3, which is 6. Alright, so that here is equal to 6. So we find ourselves with the distance is equal to 6 divided by 360 times the radius times the angle. Alright, and that gives us the distance is equal to the radius times the angle divided by 60. Alright? And we will keep that in mind for now. So let's move aside and let's redraw our situation. We want to exit from a DME arc. Let's say we have the station right over here, and we want to exit on radial 0.45. All right, we'll do something like this. All right, that's the arc. All right, and we want to exit on radial 0.45. So what we're going to have to do is to actually start turning before reaching radial 0.45 in order to turn like this and intercept and continue on radial 0.45. So we will actually need to start before reaching radial 0.45 like this. All right, and we want to know the radial on which we will start turning. All right, so we'll turn at a rate 1 turn, all right, or at 30 degrees depending at the speed at which we are actually flying. All right, but let's assume for now that we are flying at rate 1 turn, so 3 degrees per second. If we don't stop our turn right over here and we actually continue turning, we will see that as in the beginning of this video, we will do a circle. All right, well, that's not a very a perfect circle, that's more like a potato shape, but you will get the principle. All right, and we see that the distance that separates the point of anticipation right over here and the point where we will reach the radial is actually equal to the radius of turn. All right, so the distance right over here is actually known. All right, we have already calculated it at the beginning of this video. So now we will take back our formula right over here and we will move it right there. The distance is equal to the radius times the angle divided by 60. All right, so what interests us is actually the angle right over here. And from that we get that the angle is equal to the distance times 60 divided by the radius. All right, we know the radius normally. If we do a DME arc, it will normally be given by the chart. All right, and we actually know the distance because it is actually what we have calculated when we entered the DME arc. All right, so we have all the elements required in order to calculate the angle to anticipate the radial on which we will exit the DME arc. All right, so for example, if we are going at high speed, and by high speed I mean we are going at 200 knots or greater, we will need to do a turn of do the turn at a bank angle of 30 degrees. All right, so when we entered, I will write it echo. When we entered, actually no, I will write it completely. when we entered the DME arc, we calculated that in order to anticipate our turn, we needed to take our ground speed divided by 100, and then we needed to remove 1 out of the result. And after that, we had to add 0.3 in order to compensate the distance that it would take to pass from a state where the aircraft is straight and level to a state where the aircraft is making at 30 degrees. All right. So for the exit, we want to take the result of all of that, which actually is the distance. All right. It is equal to this distance right over there. Instead of actually calculating the distance that we need to anticipate before turning in order to enter the DME arc, we actually move the situation by 90 degrees, all right, and that will give us something like this, up and like that, right? Instead of having to move on the radial and turn on the side, we will turn on the side and then arrive on the radial. All right, and we will need after that to take this result over there and insert it in the formula. So that times 60 divided by the radius. So for example, if we are going at 220 knots, all right, so 220 knots of ground speed, all right. In order to enter the DME arc, we will need to take 220 divided by 100 and then remove 1 out of it, which will give us 2.2 minus 1, 1.2. All right, and then we will need to add 0.3, which will give us 1.5. All right, 1.5 is equal to 3 divided by 2. All right, and in order to know the angle of anticipation before exiting the DME arc, we will need to take 3.2 times 60 and all of that divided by the radius, which will be equal to 60 divided by 2 makes 30, all right, and 30 times 3 makes 90, which makes 90 divided by the radius in our case. All right. Let's say, for example, that our radius is equal to 15. All right. That would make 6. All right. So we will actually need to start turning 6 degrees before reaching the radial on which we want to exit the DME arc. So right now we want to exit on radial 045. So we will need to start turning when crossing radial 039. All right, and there's a difference of 6 degrees. All right. When you are flying at low speed, and by low speed I mean that you are actually flying at less than 200 knots, all right, which requires you to turn actually at a rate 1 turn. All right, let's say you are flying at 120 knots of ground speed. In order to enter the DME arc, you have calculated that you want to take your ground speed and divide it by 200, which will give you, in this case, 0.6. But you also need to add, in this case, 0.1. It can also be 0.2 if you are flying above 140 knots. But in our case, we are between 80 and 140 knots, so we only need to add 0.1, which at the end of the day gives us 0.7. All right, and then we insert it into the formula, and that will give us 0.7 multiplied by 60 divided by the radius. All right, and that gives us 42 divided by the radius. So let's say, for example, that we are doing a 12 DME arc. All right. We know that 3 times 12 equals 36, and we know that 4 times 12 equals 48. All right. So we actually need to turn between 3 and 4 degrees, and in order to avoid overshooting the radial on which we want to exit the DME arc, we will take the highest of the two. So it will be 4 degrees, roughly 4 degrees. All right, so we will need to start turning 4 degrees before reaching radial 045. So it will be, I will write it in blue, we will need to turn at radial 041, which makes sense because as we are flying slower, we will need less distance in order to perform our turn. All right, I would like to point out the fact that in the case where we are in the low speed situation, we can actually find another formula. So we had the formula which is equal to the angle is equal to the distance or the radius of turn times 60 divided by the radius of the arc. All right. Normally the distance is equal, as we wrote it before, to the ground speed divided by 200, and to which we will add 0.1 or 0.2 depending on our speed. All right. Let's forget for a moment that we need to add 0.1 or 0.2. In this case, if we replace the distance by the ground speed divided by 200, we will get something like this. The angle of anticipation will be the ground speed divided by 200 multiplied by 60 divided by the radius. All right, which at the end of the day gives us 6 divided by 20 multiplied by the ground speed divided by the radius. All right. 6 divided by 20 is equal to 3 divided by 10, all right, which gives us 0.3. But 0.3 is more or less, is roughly equals to 0.3333 and so on. All right. Usually we do the thing the other way around. Usually we say that 0.3333 is roughly equal to 0.3. But right now we will do it the other way around. So, and 0.33333 and so on is actually equal to 1/3. All right. So at the end of the day, we can say that the angle is equal to 1/3 of your ground speed divided by the radius. All right. So I will write it again. Angle is equal to the ground speed divided by 3 times the radius. All right. And if we compare it with what we have found right here, we said that we were going at 120 knots, so it makes 120 divided by 3 times 12. So 120 divided by 3 makes 40, which is equal to 40 divided by 12, which makes roughly between 3 and 4. All right, and we take the highest of the two, so it will make 4 degrees. All right, it's let's say a simpler way to calculate all of that, and calculating it using that way usually requires to keep what you have calculated at the entry of your DME arc. Right? You will need to recall this number right over here, and then to use this formula. All right, so that's the way of doing things. All right, so we now have a chart of Kefalonia Airport in Greece, and we are going to perform Garta 1 Tango departure. All right. So let's say for a second that we are flying in an A320 or in a jet. All right. Let's say that we have a ground speed of 270 knots. All right. In order to enter the DME arc, we will need to take our ground speed divided by 100 and then subtract 1 and then add 0.3. Alright, so 270 divided by 100 gives us 2.7, minus 1 it gives us 1.7, and then plus 0.3 it gives us 2. Alright, so we will need to start turning in order to enter our arc 2 nautical miles before being on the arc itself. Alright, so the arc is a 19 nautical miles DME arc, and we will just need to turn at 17 nautical miles, which is what we have right over here. Alright, then in order to exit the DME arc, we will take what we have found right over here and put it in the following formula. So we take that, we multiply it by 60, and we divide it by the radius of the DME arc, which is 19. And for the purpose of calculations, we will round it up to 20. Alright, so we remove 1 0 here, 1 0 here. It gives us 2 divided by 2, which makes 1 times 6, which is equal to 6. Alright, so we will need actually to start turning in order to exit the DME arc 6 degrees before the radial itself. So we are supposed to exit on radial 018, and we will start turning 6 degrees before reaching it. So it will start turning on radial 012, alright, which is more or less what we have right over here. The chart was telling us to start turning at on radial 011. Right? I will just erase that. Right, now let's say that we are flying much slower. Let's say that we are in a DA42 and that we are flying at a ground speed of, I will do it slightly higher, we are flying at a ground speed of 150 knots. Alright? So in order to enter the DME arc, we'll need to take our ground speed, 150, divided it by 200, and then add 0.2, because we are between 140 and 200 knots. Alright, so 150 divided by 200 gives us 0.75, plus 0.2, it gives us 0.905, which roughly equals 1 nautical mile. Alright, so we will need to start turning in order to enter the arc 1 nautical mile before reaching 19 DME. So we will need to start our turn not at 17, but at slightly higher. I will put it here, right over here. We will need to start our turn at 18 DME. Alright? Then, in order to know the radial on which we will need to start turning in order to exit the arc, we have two solutions. The first one uses all of what we have calculated until now. Alright, so we will take the result that we have right over here and do as we did for the case where the airplane is going very fast. So we take 1, we multiply it by 60, and we divide it by the radius of the arc, which is 19, but we will round it up to 20 once again, which gives us 3 degrees. Alright? And if we use the second technique, which is specific to airplanes that fly at ground speed lower than 200, we can disregard all of what we have seen right over here, and we can just take the ground speed, which is 150, divided by 3 times the radius, which is 20. Alright, the 0 goes out, the 0 goes out here, and it gives us 15 divided by 3, which is 5, and 5 divided by 2, which is 2.5. Alright, and we will round it up to 3 degrees, which is what we have found before. Alright, so instead of turning on radial 012, we will start turning 3 degrees before radial 018, which would give us radial 015. Alright, and of course, when you turn at 18 DME or on radial 015, you will need to turn at rate 1, right, which is equal to 3 degrees per second. Alright, and if you turn at 17 DME or on radial 012, alright, of course the speeds have changed, but in the case you have to use the formulas that you have used in order to calculate your anticipation. You will need to turn at 30 degrees of bank angle once again. Alright, now let's try it in the sim. And we are now in an Airbus A320. We have a ground speed of 27 and 0 knots. Alright, we are tracking the DME arc. We keep the head of the needle at 90 degrees from our heading because we have no wind. We are at 19 nautical miles from the station. I will correct the altitude. We are supposed to exit on radial 018, which is set right over here, but we said that we were going to anticipate the turn on radial 012, which we set now, and when we will cross it, we will start turning left. Right, and here it comes. And we turn. Not now, now. Here we go. Alright, 30 degrees. We keep the altitude. And we can already set our radial, which is radial 018. Like this. 30 degrees of bank. And the CDI is captured. And we can slowly start rolling out. Like this. And we are now on radial 018 after doing a DME arc. And now we are in a situation where we are flying at roughly 150 knots of that's true airspeed, but as we have the wind, that's also our ground speed. Alright, the radial 018 is set, but we said that we were going to anticipate on radial 015, right, which is coming in a few seconds right now. Alright, I will maintain the altitude and keep track of the DME arc. We are at 19 nautical miles from the station, so we are on track. I need to be careful to avoid getting the head of the needle below the reference. Alright. I will increase the power in order to keep true speed of 150 knots. And now we are passing radial 015. And we can start turning at rate 1, so 3 degrees per second. And we can set the radial 018 right over here. And we can start rolling out slowly. Like this. Alright. And so this is the end of this lesson. Thank you very much for watching almost 2 hours of video. You can leave a like or a comment if you find it useful, or if you have any kind of suggestion. In the meantime, you can find some charts in the background that might allow you to train yourself on a simulator. And I wish you good luck for your skill test.